Okay, next we have version C of the homework. So we're going to start off with those. And our first molecule for that homework set is AsH3. As is arsenic. Arsenic, we have 3 hydrogens, so we have trihydride. So arsenic trihydride is the name of our molecule. Let's see how many electrons first each of these brings to the table so that we will be able to draw our Lewis dot structure. Arsenic is in group 5, so it's bringing 5 electrons. Hydrogen is in group 1, so each of those is going to bring 3 electrons. So our total is going to be 8 electrons. Hydrogen can't be our central atom, so we're going to make arsenic our central atom. Okay? All right, and it's bonded to 3 hydrogens, so we're going to give it the bonds to the hydrogens. And how many electrons have we used up? 1, 2, 3, 4, 5, 6. Hydrogens are happy because they only need 2. We still have 2 left over, so we're going to give that a lone pair on the arsenic. Okay, so here's our Lewis dot structure. We have everything happy. There are 8 on the arsenic. 1, 2, 3, 4, 5, 6, 7, 8. Arsenic's happy, and the hydrogens are all happy with their 2. Okay, so let's find out what kind of bonds these are. We are dealing with arsenic, which has a electronegativity of 2.0, and hydrogen has an electronegativity of 2.1. So we have a 0.1 for our bonds. Okay, so it is, even though this is pretty low, right? It is slightly polar, very slightly polar. So it's closer to a non-polar, but it is slightly because just of the way this, the hydrogens and the arsenic relate to each other. So we're gonna call it slightly polar, but it's basically non-polar. We're going to now look at the shape of this molecule. So you can look at the tables. You have 3 bonded atoms and 1 lone pair. And when we have 3 bonded atoms and 1 lone pair, we essentially have something like this with the, get my lone pair on top here, my lone pair up here. So the lone pair is going to be pushing the other 3 out of a planar arrangement so that they can't be trigonal planar, and that's going to create the trigonal pyramid shape. So let me use a different color here. Trigonal pyramidal. And you guys can't see what I just wrote. There we go, trigonal pyramidal shape. Okay, so again, when you have 3 bonded atoms, and so you're gonna need a central atom that has at least 4 holes in it here, so that you can actually create this shape. But you're gonna have the 3 hydrogen atoms that are coming up. Let me change this to hydrogen atoms just so this looks better. Hydrogen is usually white, so let's make that look a little bit nicer. Okay, so there we go. Our central atom has to be, it doesn't matter to me what color because sometimes the kits didn't come with the right amounts of the different types, so you don't actually have an arsenic colored bead. But in this case, you just want one that has 4 equally distributed holes in it. And then you're gonna add your 3 hydrogens and your lone electron pair. Okay, and that will end up creating this trigonal pyramidal shape for you. Okay, so it's 3-dimensional. You can kind of see that here as I move it around. Okay, and the bonding angle is 109. Okay, so there you go, arsenic trihydride. Okay, so this one is going to be our second one in homework C, silicone tetrachloride. Silicone, and then the 4 for the chloride makes it tetra chloride. Okay, so silicone tetrachloride, and we need to figure out how to draw the electron configuration or the Lewis dot structure. So silicone, we have to figure out where it comes from. It comes from group 4 on the periodic table, so it's going to have 4 electrons coming into this equation. Chloride is in group 7, so it's gonna, each of these 4 are gonna be bringing 7 electrons. So we're going to have 28 electrons there, and then we add those together, we have 32 electrons total, okay? All right, our central atom is going to be the silicone because silicone came with fewer electrons to begin with, and I'm going to move it up a little bit higher so you can really see that silicone, and we're going to be distributing the 4 chlorides around it to start with, and I'm going to circle them in green because you're going to use green beads for those guys. Okay, so silicone now, as you can see, has 8 electrons around it, okay? And of our 32 electrons that we started with, we've used up 1, 2, 3, 4, 5, 6, 7, 8, right? So we have subtracted 8 and we got 24 left. And each of these 4 chlorides wants just 6 more, right? So how convenient. We can give each one of these guys 6 electrons. And we've used up our 24 remaining electrons. So there's our happy silicone tetrachloride. Silicone tetrachloride, now we need to look at the polarity of the electronegativity differences rather between the different atoms so that we can figure out what type of bond we're dealing with. Silicone has an electronegativity of 1.8 and chlorine has an electronegativity of 3. So our difference there is going to be 1.2, which is a fairly big difference and is definitely going to be a polar covalent bond. Now, just a point of reference here, this is a very non-polar molecule just because these chlorines are so evenly distributed around the silicone. So even though they have polar covalent bonds, the molecule overall is a non-polar molecule. Now, let's look at the shape of this guy. I've used one of the black carbon beads here from the set because, as you can see, carbon and silicone are in the same group, and so they both have the 4 holes, so you can just use one of the carbons for this. Then you're going to put in the 4 bonds for the chlorides, and you can see that you have a beautiful tetrahedral shape here. When you have 1 central atom and 4 bonded atoms, no lone pairs, you get a tetrahedral shape. Tetrahedral. Okay, so for this one, this is kind of a special ion again. So the naming is going to be a little different. This is a cyanate ion. A cyanate ion, okay, because of this negative charge here, okay? And this is, again, one of those polyatomic ions that you should have seen in your table. So we're kind of doing something a little different with these guys, okay? So we will look first at how many electrons we're dealing with in order to draw the Lewis dot structure. So first of all, we're looking at oxygen. Oxygen is in group 6, so we have 6 electrons there. Carbon is in group 4, 4 electrons there. And then we have nitrogen. Nitrogen's in group 5, so we have 5 electrons there. And we have an additional electron because this is a negative charge. So we have an extra plus 1 electron for that charge. Okay, so now we have a total of 10 and 5, 15, 16. So 16 electrons that we have to distribute around this molecular structure. Carbon came with the fewest, so we're going to make it our central atom. And then we're going to bond it with the nitrogen and the oxygen, okay? And so you can see we've used up 4 electrons to begin with here. And we are then going to give oxygen its full valence because it's more electronegativity, or it's higher in its electronegativity. So we're going to give it its ions because it wants our electrons even more, and it's going to hold on to them even better, okay? Then for the nitrogen, we can give it all its electrons as well, right? We'd have just enough. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? That would work. But carbon isn't really happy with this arrangement, right? So in order to make sure carbon and nitrogen are happy, we're going to shift some of these pairs so that we're sharing some with the carbon. So we're going to move this guy over here, and we're going to make an extra bond with the carbon and the nitrogen, okay? Now carbon's got 6, okay, and nitrogen still has 8 going around it. But carbon still doesn't have enough. So we're going to take one more pair and share it with carbon. Okay? And I think we mentioned in the lecture, nitrogen often can form double and triple bonds because its electronegativity isn't so high. So here we have now a really happy nitrogen. 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. And carbon also happy, 1, 2, 3, 4, 5, 6, 7, 8 around it. Oxygen happy, we have 1, 2, 3, 4, 5, 6, 7, 8 around it. And the oxygen, because it has the higher electronegativity of these 3 molecules, is going to be the one that hogs that extra electron the best. And so that's going to be our electric end of the, our negative end of the molecule, which makes it an ion. Okay, so there's your Lewis dot structure. And then we can look at the types of bonds here, and that is going to be by looking at the electronegativity. So the electronegativity between carbon and nitrogen, carbon has a 2.5 electronegativity and nitrogen has a 3. So if we subtract there, we have, what am I trying to do here? We have a 0.5, which just barely makes it polar, right? And then for oxygen and carbon, carbon again has the 2.5 and oxygen is 3.5. Okay, so it has a 1 difference. So we have a polar, definitely polar covalent bond there, and this is closer to non-polar, but it's still polar. So together they are polar covalent bonds, okay? And the shape of this critter is going to be, we have carbon, and this is going to be tricky. I'm not even sure that our model will let us do this, but we're going to try here. We have a double bond here, or a triple bond with the nitrogen. So we're going to have 3 of these guys going to the nitrogen. And I'm going to try and make that happen. Let's see if I can get it to work with this molecule. You have to find one of this is going to work. Right. And then we've got the single bond here with the oxygen. And the reason that we again made the triple bond with the nitrogen instead of with the oxygen is that oxygen is much more electrically negative and tends to hog the electrons more. So it doesn't share them as nicely with carbon as does nitrogen. Okay, so here I'll hold this in the same orientation as our molecule form, our Lewis dot structure here. And here you got your oxygen, your carbon, and your nitrogen. And I've showed the triple bonds here. Okay, so you can see if you have 2 bonded atoms and there's no lone pairs here, they're all shared nicely, we end up with a linear molecule. Okay, so let me just slide our paper up here so we can see what I'm writing. There we go. Our shape then is linear. Okay, for the cyanate ion. Okay, so I hope you had a little bit of fun doing something a little bit different than our normal moleculars with the ion here. All right, we're moving on. Okay, and then our next one is, okay, so the next one here is our ion, our challenging little ion here. It is a chlorite ion, okay? Chlorite ion. And we're gonna go into a little bit of a deep dive on it, this one. So I'll show you what I would expect you to do, given what we know about molecules and their structures. And then I'm gonna show you why it's not actually like that. But I'm not gonna expect you to have done that additional step. Okay, so chlorite ions, though, are a little bit special and kind of fun. So let's look at the electrons that they're bringing. Chlorine, the first thing there, is gonna have 7 electrons. So hopefully you can see everything that I'm writing here, 7 electrons. And then the oxygen each has 6 electrons because they're in group 6 and there's 2 of them, so we got 12 electrons there. And it is an ion, so it has 1 more electron. So that gives us a total, and it has a negative charge on it, 1 negative charge. So we're gonna have a total of 20 electrons. Okay, so let's write out what we would be looking at here. Another rule that we didn't cover because it's a little more advanced is that sometimes, of course, the central atom is the one that has the most the fewest electrons, but it's also the one that is the least electronegative. So chlorine is electronegativity of 3, and oxygen has an electronegativity of 3.5. You can see that on the table here. Here's chlorine 3 and oxygen 3.5. So the least electronegative is chlorine, and so that's going to end up being our central molecule, our central atom. Okay, so we're going to have it bonded to 2 oxygens on either side. And I'm going to do in green what I would expect you guys to have done. You got 20 electrons. You're going to have a bond with each of these. That brings it down to 16 electrons. We're going to give each of these guys 6, right? And that brings it down to 8 and 8, 16. So we have 4 electrons left. We're going to give those to the chlorine, and everybody's happy, right? This guy has 8, this guy has 8, this guy has 8. We think we would be done at that point. And if that's what you did, you are 100% okay, because that's what we discussed in class. So I would expect you to do this much. I'm going to show you why this is incorrect for this particular ion in just a second here. So what we have to consider is a new concept called formal charges. Formal charges, and formal charges are equal to the number of valence electrons minus the number of bars and dots. I'm just going to put a B here for bars and dots, D for dots here, that you see around that atom. Okay, so let's look at the formal charges here. And the special thing about chlorine is that it can handle more electrons around its center than again, it's one of those exceptions to the valence rule. So we're going to first calculate the formal charges on each of these. So the oxygen, let's do this in red. The oxygen's formal charge is going to be equal to its valence electrons, which is usually 6, right? Well, it is always 6 actually, minus the number of bars and dots around it. So we have 1 bar, and we have 1, 2, and this should be plus here. 1, 2, 3, 4, 5, 6 plus 6 dots. Okay, so 6 minus 7 is equal to -1, right? So there's a -1 charge, formal charge on this oxygen, and also on this oxygen, because they're mirror images of each other. The chlorine, let's do that guy in green, just so we have a difference here. The chlorine has a valence of 7 electrons, right? And it is going to, in this case, we have 2 bars around it, and we have 4 dots. Okay, so if we subtract that, we're going to get +1 because we had 6 here, right? So this would be the formal charge on the chlorine. This would be the formal charge on the oxygen. We want to have lower formal charges, okay? That we generally would like to have them much closer to 0. So let's rearrange things a little bit and see if we can fix that. Let's take out, I'm going to use another color here to just show what we're doing to change it. Let's take out one of these pairs and put it over here. Okay, let's just see what happens there. So if we have only 4 dots here and 2 bars, 4 dots, change the numbers here for the oxygen. Now we have 6 minus 6, and it gives us a formal charge of 0, which we want, right? That's a good thing, less formal charge. For the chlorine now, we have the 7 valence, and we have 1, 2, 3, 3 bars. So we're going to change that to 3, and we have 4 dots still. So if we subtract 7 from 7, we end up with a 0 here as well. Okay, so this form, and I'm going to just write this up here now, is the actual formula for the chlorite ion, because of this additional information with the formal charges. So again, if this was like, what? Don't worry about it, because we're not going to be testing you on that at this point either. This would be something you'd want to know if you went into further, more advanced chemistry. Okay, but let's put the dots here, here, and here. Okay, so this would be the formula for the chlorite ion here. And it's still going to have, like this last oxygen, we didn't change it, right? So it's going to still have a -1 over here, which we want because we have a negative ion with a formal charge that's negative. Okay, so this would be what we end up with. Okay, I know that was kind of, again, a little bit more advanced than what we talked about in our lecture. So again, like I don't expect you to have all of that necessarily nailed down and figured out entirely, because the formal charges is something you'd face in another class a little bit later. But for fun, this is the chlorite ion that we've been talking about. And then the shape for the chlorite ion is a little extra fun. We're not going to be able to use the green chlorides for this. We're going to have to use one that has a few more holes in it. So I'm going to use one of our carbons because it's got 4 holes. Yeah, there we go. So I'm going to use a carbon for the central chloride here. And then we're going to be putting find a few extra bonds here. We're going to have a double bond for that one oxygen. So let me work on getting you the shape here. Of course, you have a 2 bonded atoms and 2 electron groups, lone electron pairs, I mean, and that's going to create a shape that we have talked about, right? So we know that it's going to be a bent shape because we have 3 bonded atoms there, or 2 bonded atoms to the central atom, so 3 altogether. And I'm just finding my oxygen here. There we go. Okay, so we got this, and then we would have electron pairs that would be, okay, this is wrong. This is the wrong center atom. It only had 3. No, it does have 4. What am I doing? Oh yeah, but it's got the bonded pair. That's what happened there. Okay, so because of the bond and that, I can't show both of the electron pairs here, but we have the electron pairs are going to be pushing this out, and we would actually have another a free electron one here, but I don't have, oh, you know what? Let me do this one. This one has 1, 2, 3, 4. There's got to be one that I can show you this with. Yeah, okay, perfect. Let me actually show you what this looks like. If you have a molecule that has a little bead, rather, that has 5 holes in it, we can show you this. So we have 1 bond with oxygen. We have a double bond with another oxygen. Double bond with this other oxygen, right? And then we've got the 2 lone pairs. 2 lone pairs here. And you can see how that would create this bent shape a little bit better, right? And that is the shape of this chlorite ion, okay? Because we have the 2 lone pairs and the 2 oxygens, one with a double bond, one with a single bond here. So our shape for the chlorite ion is bent, because even though these guys would make it more of a, a 3-dimensional shape, we don't have a 3-dimensional shape because we only have the 3 atoms. So they're all right. Last one for homework C. We have this formula, and the way we have learned to name it so far would be dicarbon dihydrogen, or hydride, I should say, hydride, right? Dicarbon dihydride. But in fact, this is an organic molecule, which is ethylene. Oh, sorry, ethine, which we don't need to know because this is organic chemistry. But so you know, it is something that you will see for sure if you move on into the organic chemistry side of things. All right, but to look at this, we need to know the electron numbers, of course. And so carbon has 4 electrons. There's 2 of them. So we're going to have a total of 8 electrons from that. And then our hydrogens each have 1, and we have 2 hydrogens, so 2 electrons. Okay, so 10 total electrons in this molecule. So, sorry about all my marker moving. The carbons are going to they're going to hang out in the middle together because the hydrogens can't be in the middle very well. They can't do very much bonding, so they almost always get pushed off to the sides, okay? So the hydrogens are going to be out to the sides, okay? And we have 10 electrons to distribute, and that's not very many electrons when you got 4 atoms here, right? So let's first bond these hydrogens, and we know the hydrogens will be happy because they only need 2 electrons, and each of these bars represents 2 electrons, right? So the hydrogens are happy. Now we got to just worry about the carbons. And we just used 4 electrons, right? So we had 10, and we've used up 4, we have 6 left. And each one of these carbons is going to want all 6, right, in order to fill its 8 valence electrons. So in order to give them all 6, we have to put all of them into shared bonds, right? 2 here, 2 here, 2 here. If we try to put them in any other way, they're not going to be able to get enough electrons each. So this is what we end up with. A triple bond between the 2 carbons and a single bond with the 2 hydrogens on the outside. So let me see if I can show this very, very well. Okay, this is a carbon. You know what, let's talk about the type of bond we had here too. We didn't really talk about that in my last question. Oh my goodness, I'm gonna have to go back to that one too. Okay, so we have 2 carbons here. They're usually the black ones with 4 holes. And 2 hydrogens. 2 hydrogens. Where's another hydrogen here? And 2 hydrogens. Okay, so we're kind of started there, and then we're gonna need these little wiggly ones to make our double bond. There we go. Okay, so we got all the bits and pieces. Let's talk about the type of bond we're dealing with by looking at the electronegativity. Carbon's electronegativity is 2.5, and hydrogen's electronegativity is 2.1. So this gives us a total of 0.4, which is going to be non-polar. Non-polar covalent. Non-polar covalent bond. And let's put them together so we can see the shape that we're gonna have. Oops, this one does not have 4 holes. Some of your carbons, be careful. You got some of your black beads, which should be fun and easy to work with, have more holes than they should because of, again, some more advanced chemistry that we're not going to be too concerned about at this point. But let's put our triple bonds here. Oops, see, that one doesn't actually have 4 holes. Find one with 4 holes. Here, this carbon only has 3 as well. Come on, one of you gotta have 4. Okay, there we go. This one has 4 holes. So you got 2 carbons, or 2 of these little black beads with, in fact, 4 holes each, so that you can actually get your triple bond in here. There's your triple bond, and then you have 1 hole each sticking out over the back to get your hydrogens in. There we go. So you can see this is going to be a very nice linear molecule. And we know that because our central, if either one of the carbons has 2 things bonded to it, right? So it's going to be linear here, okay? If you look at this one as a central molecule, it's going to be linear because it's bonded to just 2 with no lone pairs. And this one here is also bonded to just 2 with no lone pairs. So that's the shape we end up with. A linear molecule, non-polar covalent bonds, and this is our Lewis dot structure. Okay, so hopefully we managed to get through that without too much stress, and I look forward to talking to you guys about it in class later. Take care.